Hello again. We continue the discussion on chain rule in this video. We'll deal with a more general case that allows us to formulate chain rule under different scenarios. To do this, we will rely heavily on the tree of dependency. So this is the statement of the general chain rule. Let U be a differentiable function of n variables. Suppose these variables are labeled x sub 1, x sub 2, up to x sub n. Suppose further that each variable x sub I is a differentiable function of m variables. Let's label these variables as t sub 1, t sub 2, up to t sub n. Then, u is also dependent on the variables t sub j, and this function is also differentiable. This allows us to compute the partial derivative of u with respect to t sub j. How? Our tree of dependency now looks like this. We have the variable u on top here. We have branches below pointing to the x sub i's. So we have x sub 1, x sub 2, up to x sub n here. Under each x sub I, we have sub-branches pointing to the t sub j's. So we have here under x1, t1, t2, up to t sub m. Same is true for x2, and so on, up to x sub n. So now, to get the partial of u with respect to t sub j, we look at the paths that start from u and end at our chosen t sub j. So let's say t sub j here is t sub 2. So we look at the paths from u up to t sub 2. So we have this path here, this path here, this path here, and so on until you get to there. So this is for the general case. The partial of u with respect to t sub j will be equal to the partial of u with respect to x sub 1 multiplied with the partial of x sub 1 with respect to t sub j. Add that to the partial of u with respect to x sub 2 times the partial of x sub 2 with respect to t sub j. Plus, you get the idea. We continue that until we reach the partial of u with respect to s sub n times the partial of x sub n with respect to t sub j. All right, so let me give you a few moments to look at the formula. If you need more time, pause this video now. So let me just warn you at some point, whenever you see a case when there's only one branch under a variable, so let's say there's just one branch under x sub 2, then you just replace the partial derivatives with the usual derivative. So instead of the partial here, you will get the derivative of x with respect to t sub 2, for instance. If there's only, but that's only for the case when there's only one branch under a certain variable. All right, so let's look at one example. So we have here, write out the chain rule for the following case when z is equal to z of x sub xy and x is equal to some function of r, s, u, and v. The same is true for y. Y is a function of r, s, u, and v. So this is the tree of dependency for this particular example. So we have z dependent on two variables x, y. So we have two branches here. And then x depends on four variables. So that's why we have four variables here. The same is true for y. Y depends on four variables. So we have four branches here. So we have four formulas for chain rule to write out here because z will depend on these four variables as well. So the partial of z with respect to r. So we look at this path and this path here. All right. So when we write that down, the partial of z with respect to r will be equal to the partial of z with respect to x times the partial of x with respect to r plus the partial of z with respect to y times the partial of y with respect to r. So now what about the partial of z with respect to s? So we have this path here and this path here. So that will be the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. Similarly, we can write the partial of z with respect to u. So we're looking at this path here and this path here. So that will be the partial of z with respect to x times the partial of x with respect to u plus the partial of z with respect to y times the partial of y with respect to u. And lastly, we can write the partial of z with respect to v. So we have this path to consider and also this path as well. Okay, so that will give me the partial of z with respect to x times the partial of x with respect to v plus the partial of z with respect to y times the partial of y with respect to v. All right, let me give you a few moments again to look at the answers. If you need more time, pause this video now. Right, so we'll look at another example here. Let u be equal to x squared plus yz, where x is equal to PR times cosine theta, y is equal to PR times sine theta, and z is equal to p plus r. We want to find the partial of u with respect to p, the partial of u with respect to r, and the partial of u with respect to theta, when p is equal to 2, r is equal to 3, and theta is equal to 0. So how do we solve this? So using the chain rule, so by now you can draw the tree of dependency by yourself. We have here u dependent on 3 variables x, y, and z. And for x, y, and z, they're all dependent on 3 variables as well. We have p, r, and theta. So the partial of u with respect to p will be the partial of u with respect to x times the partial of x with respect to p plus the partial of u with respect to y times the partial of y with respect to p plus the partial of u with respect to z times the partial of z with respect to p. So what's the partial of u with respect to x? Since u is equal to x squared plus yz, that will be equal to 2x. And the partial of x with respect to p is now equal to r cosine theta. We replace the u sub y by what's the partial of u with respect to y here? That's simply equal to z. And the partial of y with respect to p, since this is our y, the partial derivative will be r sine theta. Finally, we have the partial of u with respect to z. So looking at this expression here, that's just equal to y. And the partial of z with respect to p, looking at this expression, that will just be equal to 1. Similarly, we write out the partial of u with respect to r. So that's a partial of u with respect to x times the partial of x with respect to r plus the partial of u with respect to y times the partial of y with respect to r. So take note, we're just changing the subscripts here. Plus the partial of u with respect to z times the partial of z with respect to r. So now, computing for the partial derivatives, we get this. So again, we have the partial of u with respect to x, that's 2x. But now, the partial of x with respect to r, when we look at this expression here, that's p cosine theta. So again, partial of u with respect to y is z, but this time the partial of y with respect to r, looking at this expression, that gives us p sine theta. Then we have the partial of u with respect to z equal to y, and then multiplied with the partial of z with respect to r. When we look at this expression here, that gives us 1. So last, we look at the partial of u with respect to theta. Again, what's happening is we're just replacing the subscripts here. Instead of r, we have theta. So we have the partial of u with respect to x times the partial of x with respect to theta plus the partial of u with respect to y times the partial of y with respect to theta plus, but now this part is missing because we should have here the partial of u with respect to z, but z does not depend on theta, so that expression disappears. So when we plug in, we still have the partial of u with respect to x here, but now, looking at this expression, what's the derivative of this with respect to theta? That is now equal to negative p times r sine theta. then plus the partial of u with respect to y, that's still z. But now the partial of y with respect to theta, looking at this expression here, that is equal to PR cosine theta. All right. So again, let me give you a few moments to look at the formula. If you need more time, pause this video now. So what's next? We have the following expressions for the partial of u with respect to p, with respect to r, and with respect to theta. But the problem requires that we plug in p is equal to 2, r is equal to 3, and theta is equal to 0. But if you notice, for these expressions, we have a mixture of x, p, theta, z, and y. So it's not enough to find p, r, and theta. We also need to find x, y, and z. So remember, we're going to use the expressions that we have here to find the values of x, y, and z when p is equal to 2, r is equal to 3, and theta is equal to 0. So that will give us x. So plug in 2, 3, and 0 here. So this is simply equal to 6. Y, again, plug in 2, 3, and 0 here. This, since sign 0, gives us 0. So that's equal to 0. And then finally, for z, replace this by 2 and 3, respectively. And that gives us 5. So now, we plug in 2 for p. Here, 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 here. We plug in 3 for r. We plug in 0 for theta. We plug in 6 for x here. We plug in 0 for y. And we plug in 5 for the value of z. So that gives us now the partial of u with respect to p. So once we plug in, this is equal to 36. The partial of u with respect to r, once we plug in the values, that gives us 24. And finally, the partial of u with respect to theta, when we plug in the values, that will give us 30. All right. Great. Now, look at this last example here. We have z is equal to x squared plus xy, with x is equal to 2r minus s, and y is equal to r squared plus x. This time, we're interested in the second partial derivative of z with respect to r. But of course, before we can solve for the second partial derivative, we need to solve first the partial derivative. So using the chain rule again, how do we get first the partial of z with respect to r? So partial of z with respect to r, since z depends on two variables and x and y also depend on two variables. So actually, this is similar to the case that we had in part 1, right? So this is the partial of z with respect to x times the partial of x with respect to r, plus the partial of z with respect to y times the partial of y with respect to r. So once we plug in the values, so replace this by 2x plus y, because that's the derivative of z with respect to x. Replace this by the partial with respect to r is 2, plus the partial of z with respect to y. Again, looking at this expression, that gives us x, multiplied with the partial of y with respect to r. Looking at this expression here, that's 2r. Right, let's simplify the expression. Once you distribute, that gives me 4x plus 2y plus 2xr. Right. So applying product rule, we just need to get the derivative of this expression, the partial derivative of this expression with respect to r. So we have the second partial. So this is the partial with respect to r of this expression here. So that's why we get this. So now we have 4 times the partial of x with respect to r plus 2 times the partial of y with respect to r. Plus, so this is where we apply the product rule, okay? So these are just your usual properties of the partial derivatives, but here we apply the chain rule, not chain rule, the product rule. So that's left. We consider this as the function on the left. And this is a function on the right. So that's 2x times the partial of r with respect to r plus right times the partial derivative of this, of the expression on the left. So plus r times 2 partial of x with respect to r. Right. But this, the partial of r with respect to r, we just replace that by 1. So we have here 4 times the partial of x with respect to r. Again, we look at this expression. That's why it's 2 plus 2 times, what's a partial of y with respect to r? Again, looking at this expression, that's 2r. Plus 2x times, this is 1, plus 2r times, again, partial of x with respect to r is equal to 2. So, simplifying this expression, that gives us 8 plus 8r plus 2x. Right. And this ends part 2 of lecture 1.5. We still have part 3 where we will discuss the concept of implicit differentiation. See you then.